the time for the break. This one was a bit short because of not ending well the timing at the first session, but during the session, during the breaks, you can also go to the secretary office there and pay for the fees of the registration. So don't go all of you at the same time, but take the opportunity of the pauses or the breaks for doing that. So the next speaker of the morning is Antoine Bonways from the Laboratory Fabric, and we will talk about Manybody physics with arrays of individual atoms.
Thank you, Quentin. So good morning, everyone. So usually the organizers of a Les Houches session do not give lectures. This year is a bit special because the two lecturers we had in mind for the hot vapors and the quantum many-body physics could not come. One is in Israel, the other one in the US. So essentially, Quentin and I had to take over. That's the reason why I give this set of lectures instead of Misha Lukin. So I'm just the pale replacement of Misha. All right, sorry about that. You'll have to do with it. All right, so indeed, this set of 3 lectures will cover many-body physics with arrays of individual atoms. And although the platform that we're going to discuss is reasonably generic, the idea of this set of lectures is to illustrate basic concepts of many-body physics and AMO physics using these platforms. But everything I'm going to say can be generalized to many different platforms. And as a matter of fact, we will see that in the lectures of Patrice just after this one. We already seen part of that in the lectures of Darek this morning. So once again, the idea is we use a specific system, but the concepts are general. Okay? So the kind of thing that we're going to discuss a lot is many-body physics related obviously to quantum simulation, which is part of quantum technology. It's not the only one, but it's one part of quantum technologies. And you know very well that many-body physics is this field of physics that tries to understand ensembles of interacting quantum particles. So if you say it this way, obviously, it's essentially saying it covers all physics, because as soon as you've got more than a few particles interacting, you are entering this field. So I give here a few examples that are kind of iconic of what people have in mind when they discuss many-body physics. There is superfluidity. At very low temperatures, some fluids can flow without viscosity. Superconductivity, which is kind of the same thing but with electric current. So the current can flow without resistance in a piece of material, in a copper at low temperature, not copper, but I mean some materials at low temperature. There is also all this field which is very studied in solid-state physics, which is magnetism. What happens when you want to, how do you describe the macroscopic properties of a magnet knowing the underlying microscopic interactions between the electrons of the material? But so these are traditionally the kind of thing that you encounter in a solid-state physics textbook, but of course it extends to many other systems. I mean, high-energy physics is one other example of many-body physics. Astronomy and astrophysics and cosmology is another one. I mean, a neutron star is an example of a many-body system which exhibit Fermi pressures and all this. So essentially, it covers a huge amount of situations. What are the kind of questions that people ask in this framework? I mean, usually you ask, what is the phase diagram? So what are the equilibrium properties of this system? So that's one example of questions. Now, especially in solid-state physics, people ask, how do you excite the system? What is the excitation spectrum, which is to say, how are the eigenenergies spread over the energy, over the real spectrum? So that's another question. Now there are questions also, which is what happens if you place the system out of equilibrium. I mean, in a sense, superconductivity and superfluidity are flows, so they are out of equilibrium properties, transport properties. So all these questions, of course, we know how to answer for some of them in different systems, but we do not have any general answers for any general system. And how do you try to handle this kind of, to have a microscopic understanding of these questions? Well, I mean, usually you do an experiment and you discover an effect. For example, you discover superfluidity or superconductivity. I remind you that was not predicted theoretically. It was something that was discovered in the lab before we could do the theory. And then you try to simplify the system to the extreme, because essentially a piece of material is just too complicated to be fully described. And so you write some kind of model Hamiltonian. And you believe that this model Hamiltonian has the essence of the effect you want to observe. So I've written one of them. Don't pay attention too much. I mean, there are A dagger and A because you need that in a quantum field theory. You've got some coupling between sites. You've got some on-site interactions. I mean, for those of you who have already seen that, this is the Bose-Hubbard model. But for the others, it just doesn't matter. This is a generic Hamiltonian that people write to describe properties of some type of materials. All right, and so then you've got this Hamiltonian, and you want to see whether this Hamiltonian has built-in superfluidity, for example, or superconductivity, depending on what you consider. So you need to do a calculation to check that indeed, with this model Hamiltonian, you can recover the experimental features. Okay, so it's a dual way approach. But the problem is that in many cases, this is impossible. Okay, this is impossible just because this model is just way too complicated to be calculated. And we know why this is complicated because of what Darek showed you this morning. I mean, this is the exponential scaling of Hilbert space with the number of particles which are involved in the problem. I mean, of course, if you consider superfluidity, you got essentially a mole of electrons plus interacting with many things. So it's way larger than anything you can calculate. So I just remind you that if you just take an ensemble of spin 1/2, the size of the Hilbert space, so this is the simplest Manybody system, is 2 to the power n. And the record ab initio calculation, so what people know how to calculate with the best supercomputer in those days, is between 42 and 46. And going to 50 is just out of questions when they all interact, because, I mean, it will multiply by 4 the duration of the, I mean, not 4, well, I mean, whatever it has to be, by the calculation time. Okay, so you see that the number of particles you can calculate is extremely limited. Okay, and so here I, of course, want to raise a flag, which is a very important one. It doesn't mean that we do not know how to do anything. As a matter of fact, the lecture of this morning of Darek was just trying to show how you can build approximation in order to understand complicated systems. And all the physics you've learned at universities so far is based on this approach. I mean, of course, we know how to handle equation of state of a gas, piece of material, solid state. So obviously, theorists have developed extremely sophisticated method to bypass this problem of not being able to do any ab initio calculation. So this is not necessarily a problem. However, there are many situations where this is a problem and where the approximations that people traditionally do fail. Okay? And so this is the system, this is where actually quantum simulation has a role to play. Okay? For all the others, you've got a very good approximation, and so it doesn't matter. And so this is the realm of what is called strongly correlated materials, and I will show you some example in the third lecture of that. But once again, bear in mind, it's not because you do not know how to calculate ab initio that physics is useless. As a matter of fact, everything you've learned so far was based on many approximations. So, and you've learned a lot of things so far. Okay. So in the case where you do not know how to apply all the approximations that fail, how do you do that? Well, the idea here is now to take the model Hamiltonian that you've written to describe the system and to implement it in the lab. So now you have a machine, a quantum simulator, which directly is governed by this Hamiltonian. This Hamiltonian is an approximation of the real system, but this is exactly the Hamiltonian that governs the quantum, the state of the quantum simulator. And this is due to the fact that now you can control individually particles and engineer the Hamiltonians you want. Okay? So now you assume that you can prepare the state, I mean an initial state of the system, and you calculate any evolution of the state, or you can calculate the spectrum just by applying Schrödinger equations. Okay? And so now you have the state of the system, and you need to measure the outcome and check whether indeed it has the essential features. So in a sense, you replace what you do not know how to do I mean classically on a classical computer by the outcome of a quantum simulator. So this is the generic idea of what is quantum simulation. Okay? And not everyone would agree exactly on what it is actually, but I mean this is at least the essence of how it can be described and an important feature of it. The original idea, you know that this is, I mean, I'm not sure that Feynman had exactly this in mind, but actually it came from a paper of Feynman from 82, where the guy said, well, I believe it's true that with a suitable class of quantum machines, which now we would call a quantum simulator, you could imitate any quantum system, including the physical world. So he really had in mind, in a sense, this idea of calculating idealized Hamiltonians that would represent the essence of a physical phenomenon. Okay, and so for a long time, I mean, 82, that was for you, it's ancient history, almost like the Roman Empire, but for us, not necessarily. And so at the time, it was just science fiction, obviously, because no one had in mind how to control individually particles and engineer those systems that you could study. Over the last, essentially 40 years, people have learned how to do that to a very exquisite degrees of precision, which I will illustrate, and Patrice will as well on his system. So now we can really measure, build in the lab this synthetic or artificial quantum system due to the fact that we know how to control with a well degree of accuracy individual particles. So now the goal is to engineer this artificial matter using and to implement the Hamiltonian we want to study. Okay, those are Manybody Hamiltonians. The thing which is very important now is that based on the fact that you have almost arbitrary control on the kind of Hamiltonian you can build, you are not bound to Hamiltonians that are idealization of the real world. You can engineer your own totally exotic physical system, which has nothing to do with what you would see in the real world. Okay? So in a sense, any mathematical Hamiltonian that the theorists can think of, I mean, of course, it's not entirely true when I say there are some limitations experimentally, but okay, at least in principle, you should be able to engineer and to study. Okay? So once again, bear in mind, so we've extended the field of Hamiltonians we can study based on the fact that you can engineer your own system. Okay, so what are the benefits of doing that? If you want to study a model Hamiltonian, one real asset of this system here is that now you've got a much larger tunability of the parameters of the Hamiltonian. Imagine that you want to study the strength of the interaction in a magnet, a piece of material which exhibits magnetic properties. Of course, I mean, you cannot change the interactions between the electrons. It is what it is. So it's hard to disentangle the effect of the interactions from other type of effect in the system. Here, because you've got a knob which allows you to control the interactions, in principle, you can disentangle the effect of the interaction with respect to other types of effect. Okay, so you see this is one virtue of this quantum simulation approach. That's the large tunability. You can also change the lattice constant, for example. I mean, of course, in a magnet, it is what it is. The atoms are separated by about an angstrom, and you cannot decide to put them away by 5 angstrom if you wish. This is not possible. And the second virtue is the fact that you have a new set of tools to look at the system. Okay, which you do not have in condensed matter physics traditionally. And this is especially true in out of equilibrium situation. So I will try to illustrate that, especially in the third lecture. But now let's try to see what else we can do with those engineered quantum systems. Well, there are many things we can do. Manybody physics. That's just what we've discussed. There is another field of research which is being developed, which is called quantum sensing. So quantum sensing, this is the idea that now if you use quantum state that you can engineer with a quantum simulator, this new state exhibit enhanced sensitivity, for example, to a field. Okay, so you probably all know this example, which is kind of the iconic example we always give. If you want to take an atomic clock, so this is based on an ensemble of atoms, and you measure the hyperfine interactions between two states of cesium, for example. Well, I mean, the ultimate precision you can have is governed by the inverse of the number, the square root of the number of particles that you have in your ensemble. Okay, so this is kind of the ultimate limitation. This is called the quantum noise, the quantum projection noise. It turns out that now if you use for the same number of atoms a set of atoms that are in an entangled state or a squeeze state, I mean, there are many variants around that, you can beat this quantum projection noise and go to what is called the Heisenberg limit, where you've gained a factor square root of n in the accuracy of the sensor. Okay, so then you use the fact that you can engineer in the lab some system which exhibit quantum correlation. So this is an active process. You build a system in order to beat the usual limitation of clocks. There is the other field, of course, that you are all aware of, which is this field of quantum information. So essentially, there are two subsets, quantum cryptography and quantum computing. So I will not describe that, but the idea is, once again, if you've got a machine which can engineer entanglement, so in a sense this is a generalized quantum simulator, then you should be able to modify the class of complexity of a system and be able to perform calculations that are otherwise too hard to do. And finally, from the physics point of view, there is also a very interesting question which has to do with the transition between quantum and classical. I mean, we all know that at our scale, it's very hard to see any quantum effect. It's not completely true. I mean, if you look at superfluidity, this is exactly an example of macroscopic quantum phenomena, right? But I mean, most generally, you do not see any superposition like Schrödinger cat state with a large number of particles, right? So there is this idea of how do you switch from this classical to quantum world, or vice versa. I mean, building from the quantum at microscopic level, or do you engineer a system that would keep its quantum correlation far into the classical world, which is our world? And in a sense, these questions does not have any answer, and we don't really know whether such a transition, such a boundary exists or not. So one very pedestrian approach is, okay, you just take your system, control it, grow it as much as you can, and you see whether at some point the thing fails in a way you understand or not. Something surprising arises, like at 10 to the 6 atom, for example, then it's impossible to beat, to build a Schrödinger cat. We don't know that. No one has ever done it, okay? And there's nothing in the theory that tells you that the superposition principle has to be true even at our scale. So we need to check that experimentally. All right, so in order to study all this, of course, you need a platform. And this platform, Patrice is going to illustrate on one platform just after, so a superconducting circuit. I will illustrate with atoms. But I mean, you've got many systems onto which you can do that. So neutral atoms, trapped ions, photons are the traditional systems that belong to AMO physics. And you've got also all this class, which is a bit newer because people have done a lot of progress in engineering as well in nanofabrication labs. You can use NV centers. So essentially, you just remove in a diamond one nitrogen and one carbon atom. And so there is an empty space here, and you replace one carbon by the vacant nitrogen. And this has exactly the same spectrum of a small hydrogen atom, if you wish, rescaled by the effective mass and all this. But so this is kind of an artificial atom that you can engineer and which has the same behavior to a certain extent than a real atom in free space. You've got quantum dots, so essentially places or materials where you can take an electron and get it stuck in 3 dimensions, trap it, so it acts like an artificial atom, a much larger one. It's not an angstrom size system, it's a nanometer size system. And you've got the superconducting circuits that Patrice is going to talk about. The thing which is interesting is that from the point of view of engineering, I mean, to a certain extent, you can always reduce this system to just a set of 2 levels. 2 levels are more or less complicated, but you see that if you take a piece of superconducting qubit, very clearly it's made out of many, many atoms, but for certain degrees of freedom, like the sense of rotation, the direction of rotation of the current in the loop, for example, you can decide that those are 2 states that you can encode the information on or use as a spin system. Okay? Right, so in AMO physics, back to that, there are traditionally several type of systems that have been explored, and I put on this chart some of them in terms of the coupling range, which is this J that I was talking about. I mean, we're going to talk about that again a lot. And the type of number of atoms that people have manipulated so far. So the best control system so far still, I mean, now it can be cast into doubt, but for a long time was the ions in traps that could manipulate up to 50 ions typically. Okay? And then the interactions can be scaled between nearest neighbor to essentially infinite range. And actually it's more on the infinite range type of thing, and this is an interaction engineered by lasers. And you've got then the other type of system, atoms in optical lattices. We're going to discuss that a bit this afternoon. Usually the number of atoms you can handle is much larger, typically 10 to the 4, but the interaction is really nearest neighbor. You can use in these lattices also some atoms having permanent magnets, for example. And in this case, it becomes a dipole-dipole interactions. And the kind of platforms that I will discuss here is the one based on Rydberg atoms. And once again, this is not this platform can be written under the same formalism as all the others. So this is very generic. It's just the one that we're going to discuss. Okay. Any questions so far? Do not be shy with the questions. Okay, so this is the outline of the 3 lectures. So today what we're going to do is going to be Blackboard lecture. We're going to derive, in a general way, the dipole interactions between atoms. So this is not only to describe Rydberg atoms. Actually, it will describe any type of atoms, and it will also answer the question of Patrice, which is how do you build the van der Waals interaction. So we will do the derivation of this this morning. And then in the second lecture, which will be this afternoon, we'll do a bit of Rydberg physics in order to introduce the idea, how to create arrays of atoms and look at two-body physics, which is the first step towards Manybody, obviously, looking at something which is called the Rydberg blockade. And in the last lecture, we will apply this to the Manybody physics, 2 problems essentially, which will be the implementation of spin model and the implementation of transport in the presence of interactions between the atoms. So that's what we are going to cover over the next 2 hours and a half now. Okay? All right. So now let's go to the first lecture. Comment est-ce qu'on remonte le tableau, Quentin? Je sais plus. Le truc là. Ah oui, non, il faut comme ça. Ouais. All right, so interaction between atoms. So once again, I insist, this is not specific to Rydberg state. It will be true for any type of atom. So essentially what we want to do is to understand what happens if you just take 2 atoms. Those 2 atoms are neutral objects, obviously. And so in principle, they should not interact. I mean, they carry no charges. But of course, you know that they do interact because they are not point-like particles. They are composite objects. And because of that, you can develop dipoles. So at the end of the day, what we are interested in is the interaction between 2 dipoles. OK? So we want to do that from a quantum perspective. So that's the goal, is to calculate the interaction energy of this set of 2 dipoles. Okay, so before we really do that, there is a magic word, which is the word dipole. So let's try to remember, to remind ourselves what is an atomic dipole. From a quantum perspective, obviously. Yeah? And in a sense, Darek already introduced that this morning. So the idea is the following. You just take an atom. So an atom is essentially a nucleus, which carries a charge Ze or Zq. And you've got plus some Z electrons around. Okay? So now, if you know from physics that this kind of system can be more or less solved with some degree of accuracy, and so you have eigenenergies. For the sake of simplicity, I will just use 2 principal quantum numbers. There are many others to describe that. And you know what are the position of these states. So you've got different energies corresponding to wave function psi NLM of R. Okay, think about the hydrogen atom. Alkalis are kind of the same thing. And so now, if you want to define the dipole, so once again, this is the electronic wave function that I'm considering. R being the position, if you wish, of 1 electron. If you've got many, but you need to have R1, R2, and Rn. Okay? And it's more or less complicated to build that. What is the dipole? The dipole is just the sum. I mean, if you only have 1 electron, it would be Q times R being the position between the nucleus and the electron. If you have many, of course, it would be the sum from I equal 1 to Z of Q Ri. But once again, to keep things simple, we're just going to assume to take this expression. Okay, so this dipole, of course, if you want to quantize the thing, you do what Darek told us. You just put a hat on the thing, and it becomes an operator. So now if we want to calculate the matrix element between a different state, we just calculate the matrix element in this way. At the moment, I do not specify whether n and n prime can be different. I mean, they can be equal. And this thing can, I mean, you write it as an integral, so psi NLM R QR psi NLM RTR and prime L prime. That's right. And so now one has to be a bit careful. So he assumed first that L is equal to L prime and N equal N prime. What is the value of this matrix element? Hmm? Yes. This matrix element, how much is it? I just take the same principal quantum number, okay? And I'm just asking you, what is, in case L equal L prime, N equal L prime, what is this matrix element? 0. It's 0. That's clear for everyone that this is 0? The reason why it's 0 is the following, is that QR is an even operator, okay? Which is to say that if you change R in minus R, D is changed in minus D. And if N and L are equal, at the end of the day, you've got psi NLM square QR. This is odd or even. The square is even, so actually I always confuse, this is odd. And therefore, this gives 0. Okay? So this is the parity. You need to have a different parity for the two-wave function for the dipole moment not to be 0. So that's the first thing to remember. That's what leads to selection rules. Okay, so now at the end of the day, if I want this dipole element not to be equal to 0, so dNL N prime L prime is different from 0 if L minus L prime is equal 1, 3, 5, and so on. Okay? Actually, most of the time it's just 1 in absolute value. All right. So, so very good. So now, how do you, so this is a matrix element, right? This is something that couples two states. So I have a dNL and prime L prime. This is not the average value of the dipole. So now if I want to construct the average value of the dipole, what do? I just say that the state of the dipole is a superposition of two wave functions, as it is, as it has to be. So psi, let's say, psi 1s, psi 2p. I'm just assuming that. I need to take two states with opposite parity so that there is a dipole. And I just said that the state of the atom is going to be psi 1s plus beta psi 2p. The two things do have a difference in energy, and therefore I will just write it explicitly as an oscillating term. Okay? And now I can calculate the average value of the dipole. And the average value of the dipole is going to be given no average value in psi s, no average value in psi 2, but you've got the cross terms. Okay? So at the end of the day, you will have alpha star beta e to the minus omega 0 t times psi 1s d psi 2p. So you see big plus complex conjugate. Is this clear for everyone, this? So once again, do not confuse the matrix element, which is this term, with the average value of the dipole. Okay? The average value of the dipole does oscillate with time. If I take alpha and beta, both real, what I have, so is something which is alpha beta times 2 cosine omega t 0 t times d 1s 2p. Okay? So, and you know all this from your early quantum mechanics. We can have a quick, I mean, the thing is, I will show you later an illustration of this with a small mathematical presentation. But the thing I want to tell you is that if you superpose two states, then you can create an average dipole. Okay? So, and this average dipole oscillates exactly the way you understand an oscillation classically. Okay? So, of course, there is a small problem with this, is that as the dipole oscillates, it loses energy. And therefore, strictly speaking, the idea of having written the state as a superposition of two states is not truly correct, because the thing is going to decay as a function of time. Okay? But you remember that that if you start, so essentially assuming that you got 2 IP psi 1s, if you create initially this superposition is going to oscillate as a function of time, will decay. Okay, and the decay is exactly what the imaginary part of the Green function that Darek talked to you about. I'm going to come back to this. So this is the average value of the dipole. This decay with a time which is minus gamma t, which is the lifetime of this state. Remember, though, nevertheless, that in AMO physics, gamma is on the order of a few megahertz. Typically, of course, it varies a lot depending on the transition. And that omega 0 is on the order of 500 terahertz. So it means that if you have created initially your superposition, the number of oscillations certainly doesn't look like what I've showed here. You've got a huge amount of oscillation before the decay. You've got like typically 10 to the 8 oscillations. So to a good approximation, this image is good before the system has decayed. Okay? So now, if you want to go beyond that and have a steady-state dipole, we need to do what Darek said this morning. We need to drive the dipole with a field. And this field can be either a microwave or an optical field. Okay, we're not going to do this. Then you use the Bloch equations to account for the fact that the system is not isolated and so forth. But that's not the goal of what I want to discuss. I mean, it's mainly what Darek is going to discuss. Okay? Right. Any questions so far? So bear in mind, and please do not confuse, because otherwise you'll have a hard time to reconcile pictures. Do not get confused between the matrix element and the average value of the dipole. Okay? Those are not the same thing. All right, so interactions, so dipole-dipole interaction. So, and the case I'm going to discuss is what is called the static case. This is one limit of what Darek has showed to you this morning. So what we're going to assume, I just take two atoms, and for the sake of simplicity, again, think about the hydrogen atom or an alkali. So essentially a nucleus and a charge minus q around. Okay? I'm going to say that there's a distance r between the nucleus, and this distance is frozen. So I use what is called the Born approximation, the Born-Oppenheimer approximation. The position of the nucleus is frozen in space. Okay? They do not move, the nucleus. Okay, so this is already one approximation, and it's true only because you have to compare different time scales, but okay. Then you've got the position R1 of the first electron and the position R2 of the second electron. So now if I write the Hamiltonian that describes the entire thing, what do I have? I have P1 square over 2m, the kinetic energy of the first electron, minus E square over R1, R1 between this being the distance between this first electron and the first nucleus. The same thing for the second electron. But of course, that's not all, because what I also have is the electrostatic repulsion between the nucleus. So plus E square over R, the distance between the two atoms. I have the possibility for the first electron to be attracted by the second nucleus and vice versa. So if I write all that, I will have R minus R1. So R minus R1, which is this distance, minus E square over R plus R2. and I have the electrostatic repulsion between the electrons. So this is a mess already in this simple case. So plus E squared over R minus R1 plus R2. Okay? So you see that immediately, having already 2 electrons, you have the sum of the Hamiltonian for independent atoms, but you already have many terms that pops in, even without spin, without nothing. That are the electrostatic terms. Okay, and so now we do the usual trick. We will assume that R is much larger than the typical size of the atom. This atom will have a typical size A0. In the ground state, this size is the Bohr radius. But of course, in the excited state, it can be much larger than that, as we will see. But for the moment, let's not worry too much about that. R much larger than A0. And then we do a Taylor expansion in powers of Ri over R. So I will not bother you with this. I just give you the result, okay? But you need to keep the 4 terms. And if you do the Taylor expansion, what you find is that you've got an extra, all this term, HDD, can be written in the form 1 over 4 pi epsilon naught d1 d2 minus 3 d1 R d2 R over R cube. Okay? Just one notation here, I haven't specified it. What I call E squared, this is what people do in MO physics, and this is the usual Q square over 4 pi epsilon naught. I will have a tendency to forget the 4 pi epsilon naught many times because it's just annoying to write. Okay? So this is clear. I mean, everyone has seen that once in his life, this kind of thing, so I do not need to do the derivation. And of course, if you want to quantize, well, you just put hats, same thing, on the operator. Just to connect with the previous lecture, this is nothing but the Green's function that Darek has written, keeping only the 1 over R cubed term. So what Darek had written is something of this form, d1j, which was a tensor. This is the tensor, the tensorial form. Okay? So once again, this is exactly what Dirac, not Dirac, but Darek, sorry, has derived, maybe Dirac as well, I don't know. But just keeping the static case, which is to say the case where you are, okay, sorry. First, you are in the dipole approximation. Dipole approximation means that you are far with respect to the size. Static means that you have another boundary, which is that you can neglect the wavelength associated with the transition. So static case means this. Okay? So you see that your interatomic distance for this expression to be valid should not be either too large or too small. Okay? Good. All right, so now let's look at a small toy model. And this toy model is nice because it already gives you all the essence of what is a van der Waals and what is a resonant dipole-dipole interaction. And before I do that, I just need to specify one thing, which is this operator is an operator acting in an Hilbert space, which is the tensor product of the first atom by the Hilbert space of the second atom, which is to say that the basis to write this Hamiltonian is N1, L1, M1, tensor N2, L2, M2. Okay? So, toy model. Let's consider that I can reduce each atom to a 2-level system. Okay? Just to make it simple. Do not need to specify what they are. I will call it G and E. They can, of course, be already excited state. It's not the problem. But from the point of view of a two-level system, I will have a ground state and an excited state. I have another atom, G, and therefore the basis that I need to write to describe this is G, G, E, 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 G, G, E. So this is the two-atom basis. Okay? So now if I plot the spectrum of this thing, let's call omega naught the frequency difference between the two states. Of course, I have three possibilities. I can have GG, EE, and here I can have EG or GE that are degenerate states. Okay? And so what we're going to do now, those are independent atoms. We're going to see how this spectrum is modified, where now I take into account these electrostatic interactions. Okay, and we will recover, naturally, the van der Waals interaction and the resonant dipole-dipole interaction. Okay, so this is without HDD. And the question now is to calculate the influence of the dipole-dipole interaction. Do not hesitate to ask questions. I know that usually I go pretty fast when I write, so if you need to stop me, you need to ask questions. Otherwise. All right, so now let's write in the matrix, so matrix of HDD in the basis, which is here. So on the diagonal, this is reasonably simple. I have 0, 2 h bar omega 0, h bar omega naught, h bar omega naught. So I use this order, GG, EE, EG, GE, for reasons that will become apparent in a second. Okay? And so now I ask myself, what are the matrix elements that couple those things? I mean, of course, I can be coupled here and here with a matrix element, which would be DEG. Okay? So if I calculate, I'll just give you an example. For example, let's write it here. This will be DEG square over R cube. Why is that so? Because you calculate EG D1, D2. So I just drop all the vector part and all the things just for the discussion. GE. And you see that this is the product of two matrix elements that are equal. And so this is the DEG square. Okay? Then there is no coupling to the other state. But you do have a coupling between EE and GG. This coupling is DEG square over R cube again. It's just that here I have EE, GG, so the same thing. DEG square over R cube. So this is the Hamiltonian that describes the interactions in this basis. And you see the reason why I've written it this way is because now this is a block diagonal matrix, so I can diagonalize independently, and which I will not do. I will just give you the results in perturbation theory, which is kind of the interesting thing. So let's take first the block 1. Okay, the block 1 is the one which will lead to the van der Waals interaction. Okay, so block 1. I have a matrix which is of the form 0V delta with delta which is much larger than V. Usually the coupling is much smaller than the energy difference that you have. As a consequence, you know that essentially the GG and EE states are going to be shifted in energy by a quantity which is V square over delta and minus V square over delta. This is from perturbation theory. This is the Taylor expansion of the exact eigenvalues of this thing. And furthermore, the new ground state is the initial ground state plus V over delta times the excited state, and the excited state, E prime, is E plus V over delta G with a minus sign. Okay, so now phrased with our notations. Remember, this is the EE prime, which is EE minus GG. And this is generic for any two-level system. Now I'm specific for my two-level system of two atoms interacting. So the shift in energy here is dEg square over r cube square divided by delta, delta being 2 over h bar omega naught. And here, the same, but with a minus sign. So minus dEg square over delta square, r cube over 2h bar omega naught. And here, this is the Gg, which is prime Gg plus. Okay? So what do you recover here? Well, you recover the fact that the interaction scales like 1 over R6. This is the van der Waals interaction. Okay, and here it's minus A6 van der Waals. Okay? So now let's look at the other term here. So you see, so once again, the van der Waals interaction, this is nothing but the dipole-dipole interaction in a perturbative limit, okay, of the static case. But now let's look at the second block of the matrix, the block 2, and this block now is actually, you cannot use perturbation theory because essentially you have a degenerate eigenstate, so you need to rediagonalize the thing. So now the new energies, so you look at the two energies of this problem, are going to be h bar omega naught plus or minus, because it's exactly, it's easy to diagonal, dEg over r cube. Okay? And this is called the resonant dipole-dipole interaction. And just to connect with what Darek has showed you, so now if I plot this, and I will plot the full spectrum in a minute, but essentially, as a function of R, I should have this C3 over R3 minus C3 over R3. Okay, and of course the eigenstates are Eg minus GE 1 over root 2, 1 over root 2, Eg plus GE. So in the language of Darek, this is a subradiant state, the antisymmetric combination of the excited state, and this is called the superradiant state. For a reason I'm going to give you in a second. Okay? So that's clear for everyone, this? What?
Why did you drop the other part of the Hamiltonian?
Which one?
The vectorial part. Like, I think we computed only d1, d2 over R.
Yeah. You're completely right. If I had to be careful, this term, which looks much more complicated, it would have an angular part as well, but the order of magnitude is always this. So in a sense, what I have done, I've assumed that the two dipoles are parallel with each other and that the internuclear axis is perpendicular. So that's a good question. This is a simplification, not just to write horrible equations on the board. Okay? So why is it called subradiant and superradiant? Because now if I calculate the collective dipole coupling this state to the ground state, I find 0. Let's calculate d1 plus d2. Once again, I drop all the vectorial part. 1 over root 2 Eg plus or minus GE, GG. So what I've done here, once again, in the spectrum, I have the GG. I have those two states, and I just try to see how they are coupled to the ground state, to see whether they can decay or not. And you see that because D1 and D2 in amplitude are the same, I will find root 2 DEG plus or minus, sorry, 1 over root 2 DEG plus or minus DEG, depending on the sign. Okay? So in one case, you've got a subradiant state which does not decay because it's not coupled to the ground state. There is no collective dipole associated to that. Bear in mind, we're in the static case, and the atoms are very close to each other. Soon as you bring them slightly apart, they have a non-zero state, and that's exactly what Darek explained you this morning. If you are in a chain, and you are not exactly, you do not have the two atoms sitting exactly on each other, there is no strictly subradiant state. They need to be on top of each other or very close to each other. Okay? And this one has an enhanced coupling, which is square root of 2 DEG. Okay? Ça va pour tout le monde, ça? Sorry, it's all right for everyone, this? Yes or no? Okay. So now what I would like to do is to show you that this is actually a very powerful model, because now if you take the potential curve of any real atoms, of the interactions between two atoms, you exactly find these features. Okay. So this is a molecular calculation, so it's ugly, of two rubidium atoms interacting with each other. Okay? So you have many, many states. But it doesn't matter. The gross features are reproduced by this model. You have a curve which is essentially flat before it rolls down by a 1 over R6. So any atoms in their ground state always have a 1 over R6, and it's always attractive. Okay? Based on the model we have, we could refine that. Then you've got the S plus P. What are the S plus P? If you take a rubidium atom, it's essentially like hydrogen, except that instead of having one S and two P, you will have 5S, 5P. What do you find? You find this splitting, which goes like 1 over R3. Before the atoms are too close, and then it's a mess, of course, because you are beyond the dipole approximation. The atoms are too close. You cannot only boil down the interactions to the dipole case. And then you will have the SS, which is already mixed a lot, but which essentially would be a C6 over R6. Here it's so much coupled to the other state that it's pushed down. But so, once again, it's very important to have in mind this toy model because it gives you all the physics of the interactions between two atoms, with the two possible interactions, the van der Waals and the resonant. Of course, and once again, and it's the truth. I mean, for those of you who remember their chemistry, you may remember that when you've got an orbital which is binding, you've got an anti-binding orbital. This is the binding, this is the anti-binding. Okay, so this again connects to the chemistry, so just with this toy model. Okay, so now, just to finish off, I would like to tell you what we do when we have not a two-level atom. And of course, I'm not going to do the thing in the full generality because it's a mess. But so part number 4, beyond the two-level atom case. Which is to say that I need to care about all the states of the atomic structure, so all the NLM. Okay? So now what I have in energy, I will have a state NL, NL. So this is the equivalent of the state of the first atom, the state of the second atom. Okay? And this will be coupled to many other pair states. I will have N1, L1, N2, L2, and so on and so forth. This is clear, this writing? This is exactly what we had before, if you wish. How is the state EE coupled? It's coupled to the state EG and GE. Okay, so it's just the generalization of that. And each of them, of course, are coupled by dipole matrix element, which I can calculate, and which are DNL, NL, sorry, N1, L1, times DNL, N2, L2. All right? So now if I want, and once again, the thing which is very important is that, of course, L1 and L2 differ from L by 1. They need to be of opposite parity, otherwise I have 0. So now I just apply perturbation theory, and I just write that the state NL is coupled to all the other states. Therefore, the shift in perturbation theory, it cannot be at first order, because at first order there is no dipole between the state NL and LL. So this has to be NL, HDD, NL, NL. This is 0. And this, and you have the second order, which is sum over N1, N2, L1, L2, of NL, or N1, L1, D1, NL, N2, L2, D2, NL, modulus square, over the difference in energy, so that's the square of the matrix element, divided by the energy, which is NL plus NL, minus E N1, L1, minus E N2, L2. But essentially, you recover the exact mathematical form. It's D square divided by an energy difference, which is the delta, which was our 2 h bar omega naught. It's just that you need to sum over all the states you are coupled to. And you find that for the ground state, because these states are always larger, higher in energy, this is always negative. So you recover the fact that the ground state is always attractive for any atoms. This is built in the formalism. Okay? Right, so I'm not going to, so this is all I wanted to say for this morning. Of course now, so this perturbation theory, you almost never do those days. This is good to have hand-wavy arguments. But now you can find online some interaction energy calculators. Okay, so essentially they diagonalize your matrix. So instead of being a 2 by 2, it's a huge matrix which accounts for all those states. And you do the exact diagonalization. You need to cut, of course, the basis at some point, otherwise you cannot diagonalize. So you can find those things online. So just to show you what it looks like. So let's assume, so this is one example of the you will find on the slide. Let's assume that I just take two rubidium atoms in the state 30s. This is the L. I just ask the thing to calculate. So this is an exact diagonalization, and it gives me a repulsive van der Waals form. Now I can, so they have the same parity, so that's normal that I find van der Waals, but of course I could use one which is S, the other one which is P, so let's put one here. Okay, I just ask the thing to calculate, and it generates the 1 over R cube. The big difference is that, of course, now when you fit, you immediately have built in all this sum. Okay, this is the C3 over R3. So this is the modern way to do that. Now we have computers to do this. Perturbation theory is very important to understand the underlying physics, but at the end of the day, if you want to do a real calculation, you do it this way. Okay? All right, so I think I will stop here for today. There are many other things we could discuss, but this is the essence of what I wanted to do. And this afternoon, we're going to play with that just with 2 atoms. Okay? And then tomorrow will be with many atoms. But just one quick problem that you can try to do for yourselves. Try to use what we've done. So let's, problem 1. Calculate the van der Waals interaction for 2 alkali atoms in their ground state. The order of magnitude. You will see that if you do it using the perturbation theory and all what we've done, you will find a good order of magnitude based on what we've done. So just try to do that. Just take 2 atoms at 1 micrometer and ask yourself what is their van der Waals energy. Without looking on Wikipedia, of course, I'm just doing the thing here. And comparing then to Wikipedia or to whatever you can find. And the second problem is try to come up with a classical model of the van der Waals interaction. I've done everything quantum, but there is also a classical model that will allow you to understand this. So it's also interesting to have this classical model in mind. So no quantum physics in this last thing. It's not completely true because it's kind of hidden in some parameters, but it doesn't matter. Okay? So I will stop now.
Thank you, Antoine. Any questions for Antoine?
You need a second coffee. So.
We need a second coffee. So, okay, coffee break and we come back at 11:20.
Yeah, for Patrice.